Hello everybody, my name is Ben Kravitz. I'm an assistant professor in the Department of Earth and Atmospheric Sciences at Indiana University, and I want to talk to you about machine learning, more specifically machine learning to improve climate predictability. So this work has been conducted in conjunction with quite a few people. I'm lucky enough to work with a bunch of machine learning experts at Western Washington University, also Claudia Tibaldi at the Joint Global Change Research Institute. This was work that was developed under the Multi-Sector Dynamics program, but we're working on applications where we can leverage it for RGMA, specifically looking at predictability. So I want to talk about two studies. In this first study, we asked the question, can machine learning help us have better predictability? More specifically, if we use machine learning to learn the model's internal state, does that help us? So, for example, there are lots of modes of variability, and if you get the phase of, say, the Pacific Decadal Oscillation right, that's going to help you out in predictability of the next few years. The same with El Nino, the same with various other modes of variability. So, machine learning can be a really great tool for this sort of thing because it's data-driven. It just learns whatever's in there. And so that's what we did. We looked at, so this is precipitation over, and all of these are, the y-axis is RMS error in millimeters per day, looking over the entire region. So this is polar, mid-latitude, and tropics, and then land versus ocean. So we divided up the world into 6 regions, and we looked at different machine learning architectures for what we wanted to do. So one of the baselines that we looked at is just a persistence forecast. We didn't expect it to be very good. Another baseline that we looked at is an autoregressive model, specifically AR1. And then our best model in here was an 18-layer residual network. And I'm not going to get into what that means. You're welcome to ask me later. But that one does a pretty good job out to 120 months. So we compared our machine learning algorithm against climate model output that we had. So this was a promising result. And then in the second study that I want to talk about, climate models are really expensive. But so what do we do if we want to learn things like different scenarios or looking at extreme events? So extreme events are rare, and they require a lot of simulation time to be able to fill out those probability distributions. The same with scenarios. We can only afford to run a few of them. So is there a faster way of generating new realizations? And so what we did in this study, which is in preparation, these are daily precipitation fields where we trained a deep learning algorithm, more specifically a generative adversarial network, or GAN, the hot ticket item these days. We trained that on climate model output, and then we tried to look at can we use that training to then generate new realizations of daily precipitation. So here are our results. I'm not going to tell you which one is the GAN and which one is the actual climate model. I'd like to see if you can figure that out. Nobody's been able to yet, but this looks pretty promising too. So there are some really promising applications of deep learning to improve predictability. We've explored 2 aspects of it, so forecasting, improving predictability, emulating climate models to explore extreme events so we can get predictability of rare events. We've established some techniques. They appear to work. I mean, this isn't art appreciation. We have some metrics to back this up, but there are lots more things we can do. We're working on expanding and refining these methods, but also we'd really love to hear from you if you think you can use this technique on your favorite problem. So I'm sorry I can't be here in person to take questions, but I'd love to hear from you by email. Please get in touch. Thank you.